Hi, I'm Yao, working with Dr. Hu, and today I'm going to share my research on remote detection of Karenia brevis blooms on the West Florida shelf. The Karenia brevis is a dinoflagellate and commonly found in the West Florida shelf, and the blooms will turn the water discolorations. So it is important to, so people usually call it red tide, and the red tide threatens the people's health, the marine ecosystem, the economics, and the tourism. So it is important to monitor it. And here the FWC in the past decades have tons of in situ data from the water samples, but this in situ data is not enough. You can show that the number of in situ data is very low, and it can't show the patterns and the distributions of the Karenia brevis blooms. But remote sensing with the more valid observations can. But remote sensing also have limitations, like you can see that in this enhanced RGB, the water discoloration not only from the red tides, but also from other things like river plumes, the suspended sediments and sedums, and the high color index indicate the red tide, not only the red tide bloom, but also other blooms and other things. So without the in situ data, we cannot confirm that the discoloration is Karenia brevis bloom. But with the in situ data, we can confirm that this bloom is Karenia brevis and others are not. Compare the spectral analysis, except the river plume here, and the other things shows the really close the spectral shape. So it is hard to use the pixel-wise algorithm to detect to detect or classify the pixel is Karenia brevis or not. So it is important to develop a patch-wise algorithm to delineate the bloom patch-wise out. So here, the first try we use the MODIS sensors, and we manually delineate the Karenia brevis bloom. Once the in situ data is high and the color index is high, and it turns the water discolorations, and this patches we consider it is the Karenia brevis, and we manually delineate it out. But this is too time consuming. So then a question arises, is there any method can automatically delineate these patches out? And the answer is yes. We develop a deep learning model, and this deep learning model can automatically detect the blooms out. And firstly, the first step is to train the model to learn where is red tide and where is not. Here is the ground truth, the steps we use to prepare the ground truth. With the high color index and the high in situ data and the water discolorations, we manually roughly circle these patches and then apply a threshold of color index and then mark this patch out. And combine the ground truth, the color index, and the remote sensing informations for the 6 bands from VIIRS sensors. We prepare the training data set to train the model to learn where's the red tide. And with training and validation, this validation data set is independent from the training data set. And then after training and validating, we got the model can directly apply to the VIIRS sensors. And then the output is the daily model extractor results. It classified the here the red is the red tide patches, and the other things, the blue one is other things, not the red tide or the other things, just the waters. And the green one is the no observations. And then when we got the daily model extract results, we got the we did the monthly composite and get the Karenia brevis blooms frequency and coverages. And here's the 2 examples of the validation. And you can see that with the high color index, with the water discolorations, and the in situ data shows here, and the model results are really consistent with the ground truth result. And the true negative is the high color index, the water discolorations, but the in situ data is really low. It shows that there's no Karenia brevis. and the ground truth said is no, and the model said is no. And here are two model outputs to show the model results. The circled, I circled the right-side bloom, the Karenia brevis blooms, and you can see that over here is also the high color index, and with the lower in situ data here, and the model didn't pick these blooms, not the bloom. They didn't pick these patches out. They just picked the right-side bloom out, and we compare this to spectral shape. It's really the spectral shape similarity is really close, and the model can correctly identify the Karenia brevis bloom or not. And here's another example, also the high color index water discolorations with the in situ data high and low in situ data here. And the close spectral similarities, it shows that the model can correctly get the results. And then we compare our deep learning model with our manually delineation results. Here is the big bloom in 2018, and you can see the high consistency between the manually delineated and deep learning models. But why we didn't use the MODIS? Because the VIIRS sensors have more valid observations, and it didn't get that saturated as the MODIS. So for near real time and for alert communities, it's better to use the VIIRS sensor rather than the MODIS sensor. But both MODIS sensor and the VIIRS sensor have 1 kilometer spatial resolution. It lost some details, especially for the nearshore communities. And luckily, now we have a SuperDove sensor. Since 2020, it have 1-day revisit and 3-meter resolutions, and with 8 bands, with 8 spectral bands. And here's examples. I used similar deep learning models to train the SuperDove sensor. You can see that it shows the right-side detail, very, very fine pictures and the water discolorations with the in situ data conformations. And we extracted the right-side blooms out from the SuperDove sensor and generated the weekly composite for the early 2023 right-side blooms. And these fine resolutions can help the more local communities. And this project is ongoing, and the result is compelling. And this is all the results I would like to show today about the remote detection of Karenia brevis bloom. Thank you.